In this video, I'm going to be explaining Newton's second law for a system of particles. So the diagram here shows a system of particles, and I draw a dashed line around the system of particles so that we know that that's the boundary, and everything inside the dashed line represents the system under consideration. All these particles have different sizes and are quite arbitrary in that sense. To the left of the system of particles is shown an inertial reference frame with components x, y, and z. And this will be referred to during this lesson. For a single particle, based on Newton's second law, we know that F equals ma, where F is the force vector, m is the mass of the particle, and a is the acceleration vector. Now F is a force acting on the particle, and a is the resulting acceleration of the particle. Now the question becomes, what about for a system of particles such as is shown in this figure at the top? For a system of particles which are isolated from any external forces so that only internal forces act between them, the center of mass of the system moves in a straight line at constant speed or remains stationary. So just wanted to elaborate here, external forces are due to any force that comes from outside the system. So this could be to contact with an object that is outside of the system. So if I had, say, another particle outside of the system defined by the dashed line, and it's contacting one of the particles inside the system, then that causes an external force. So it comes down to how you define your system of particles. Now, the center of mass of the system, when there's no external forces acting, moves in a straight line at constant speed or remains stationary. For the stationary case, I'm going to talk about that in an example at the end. But for the straight line case, I'm going to talk about an example right now, which most people are familiar with, and that is two colliding billiard balls. So here, what we're doing is we're looking at the external forces only in the plane of motion of the billiard balls. So you can think of it as just looking at the horizontal direction. So where even though there is actually external forces acting on these billiard balls, since they're sitting on the table and the table is contacting them from the bottom, then yes, there is an external force. But in this case, we can just look at the horizontal direction and analyze this problem um, in the horizontal direction uh, under the consideration that there are no external forces acting. So for this system here, there are only internal forces acting, and those internal forces occur when these two billiard balls collide. So before the collision, you have the diagram here on the left, and you have the center of mass, which I call point G, moving at some velocity vg1, which is a vector quantity. And after the collision, the two balls move as shown here, and the center of mass of these two balls moves at velocity vg2, which is also a vector quantity. Now vg1 is equal to vg2 because there is no external forces acting in this system. So basically, as mentioned, the sum of the external forces acting on this system is zero in the horizontal direction. So this center of mass point is theoretically located in empty space. It's just a theoretical center of mass of these two balls. So it takes a bit of visualization, but you can imagine that this theoretical point moves in a constant direction at constant speed before and after the collision. And one final assumption in this question is that we are ignoring friction with the billiard table. Otherwise, the sum of the external forces would not be equal to 0. Now, let's say that there are external forces acting on the system of particles where the sum of the external forces is not equal to 0. In that case, we can write the sum of the external forces, represented by F external, which is a vector, is equal to large M times AG, which is the acceleration of the center of mass of the system, which is also a vector. And I call this equation star because I'm going to refer to it later on. So M here, large M, is the mass of all the particles in the system. So it would be the mass of all these particles shown here in the dashed line on the top left of your screen and added together. So it's the sum of the mass of all the particles within the defined boundary. We can further write this. We can resolve this equation along the x, y, and z components of the inertial reference frame, which is convenient for solving different problems since we often deal with components along different direction. So in that case, we write F external x is equal to large M times AGX, F external y is equal to large M times AGY, and F external z is equal to large M times AGZ. So all I did was I resolved this vector equation along the x, y, and z components. Now let's look at a interesting example. Imagine you throw a hammer. Now, as you can imagine, the hammer will turn and twist in the air during its flight. Now, due to the previous equation, this equation marked star, the center of mass of the hammer moves in a parabolic path. So it doesn't matter what the rest of the hammer is doing, that center of mass point will always follow this parabolic path. Now that's because the only external force acting on this system, which consists of the hammer, is gravity. And I should mention that this assumes that we have no air resistance. And as a result, we can apply the usual equations for projectile motion to the center of mass of this hammer. So looking at the previous equation marked star, we can say that large M times G, where G is the gravitational acceleration vector, is equal to large M times A, where A is the acceleration vector for the center of mass of the hammer. Now, large M cancels out, and we're left with that the acceleration vector of the center of mass of the hammer is equal to the gravitational acceleration, which means that the center of mass of the hammer accelerates downward at G. And as well, the horizontal velocity of the center of mass stays constant since no external force is acting in the horizontal direction. Again, this assumes no air resistance. So basically what I'm saying is that the center of mass of the hammer can be completely modeled with projectile motion equations, once again ignoring air resistance. Now let's look at a simple example. Show that the equation star holds for two blocks moving together and being pushed with a force F on a frictionless surface. And this is again, there's no friction force on this surface, and you can assume it's a horizontal flat surface. So here you have the two blocks, and they're in contact, and they're moving together at a acceleration a to the right, and this is because they are being pushed to the right with a force F as shown. Now, acceleration a is of these two blocks is is the acceleration of each block, and it is also the acceleration of the center of mass of these two blocks. Now if we can imagine moving these two blocks apart and isolating the forces acting on each block, we would see that for the first block on the left, which I call block 1, there's the force F acting on it, and there's an internal force F internal acting on it to the left as shown. And by Newton's third law, this is equal and opposite to the internal force acting on block 2 as shown. Next, what I'm going to do is I'm going to apply Newton's second law for each block. So for the first block, F minus F internal is equal to m1 times A, and for the second block, F internal is equal to m2 times A, and I call these equations 1 and 2. Now, keep in mind that I'm not showing vector notation because this is a 1D problem and we don't have to use vector notation for convenience. And M1 and M2 are the masses of blocks 1 and 2 respectively. Now we can add equations 1 and 2. So we have F minus F internal plus F internal is equal to M1A plus M2A. So the internal forces cancel out and we have F is equal to M1 plus M2 all multiplied by A. So F is equal to large M times A. And that is a simple example showing that the equation marked star in the first slide is true. Now let's look at an example, and this one involves the fact that the acceleration, that when no external forces act on a system, the center of mass either moves in a straight line at constant speed or the center of mass remains stationary. In this case, we're looking at a situation where the center of mass of the system remains stationary, as I mentioned at the beginning, in which I mentioned that I'll be going through an example illustrating that. So for this example, we have person is standing on a board that is on a flat and frictionless ice surface. The man walks to the left on the board a distance d relative to the board. If the man and board both have a mass m, what distance does the board move and in what direction? So here's a picture of the man standing on the board, and the board is sitting on a flat surface, an ice surface, and the surface is horizontal. So in this case, even though there is gravity acting on the system, because we're only looking at the horizontal direction, then we can apply the Newton's second law equation for a system of particles as described in the horizontal direction. So I show G here as the center of mass of the man board system. So the man walks to the left relative to the board a distance d and then stops. And what we want to do is find how much and in what direction the board moves as a result of the man walking a distance d. So for this system, the external forces acting on it is equal to 0, which means that 0 is equal to m times ag, where ag is the acceleration vector of the center of mass of the system, and m is the mass of the system consisting of the man and board. So as a result, ag is equal to 0. Since there is no initial motion on the system, which means that the board and man are initially stationary, then the center of mass of the system must remain stationary after the man walks a distance d. So this comes from the fact that the vector ag is equal to 0. Since the man and board have the same mass, the center of mass of the system must be exactly in the middle of the center of mass of each. So I'll just draw a diagram explaining that. So initially, you have the center, you have a point here shown on the left, which represents the center of mass of the man, and you have a point here on the right representing the center of mass of the board. And each of those points is located at a distance L from point G, which is the center of mass of the man and board combined. Now this point stays at the same location in physical space, which means that after the man moves and the board moves, that this point G for the system stays in the same place. So imagine that the man moves to the left a distance d relative to the board, and the board moves to the right some distance x. Then the final distance of the man's center of mass from this point G, which doesn't move, is equal to L plus D minus X. And the center of mass of the board, which moves a distance x to the right, is then located a distance L plus X from this point G. Now, since both masses are equal, in other words, since the mass of the man and the board are the same, then this point G, rather these two distances L plus D minus X and L plus X must be equal, since G must always lie in the exact middle of the two center of mass points, since both masses are equal. So then we write that L plus D minus X is equal to L plus X. L cancels out, so we're left with 2x is equal to D, which means that x is equal to D over 2. So this is the distance that the board moves to the right. So if the board moved to the left, for whatever reason, then this would just be a negative value. So we assumed the right direction by saying that x is to the right. So in summary, for a system of particles, the sum of the external forces is equal to the total mass of the system times the acceleration of the center mass of the system. And for a special case where the sum of the external forces is 0, the acceleration of the center of mass is 0. And the two specific cases mentioned are where the velocity of the center of mass is constant or the center of mass is stationary. So this concept can be used to find the location of the center of mass of a system in motion, as done previously for the board-man system. And finally, a system can be any system with no restrictions, such as a rigid body, a deforming body, a liquid, or a gas. So it doesn't matter the nature of the system, as long as you define it, and it could either be rigid, deforming, liquid, or a gas. And that completes this video. Thanks for watching.